In this section, I'm going to explain how to calculate the concentration of electrons in the conduction band and holes in the valence band of intrinsic semiconductors. As carriers are responsible for electrical conduction, the number of carriers will directly translate to how conductive a material is. Later in this course, you will notice that a lot of the applications of semiconductor devices are achieved by electrically changing the carrier concentration at the particular locations in the material. To calculate the carrier concentrations, or carrier density, or the number of carriers per unit volume, which are the same thing, two new concepts have to be introduced. They are the equivalent density of states and the Fermi-Dirac statistics. After this, we will give the definition of an important energy level called the Fermi level. With the Fermi level defined, we can then explain how carriers respond to external voltages. The density of carriers in a solid semiconductor material depends on three factors: the density of state available in the energy band, the size of the band gap of the semiconductor, and the temperature of the operation environment. Let's start with the density of state. A state is just a space to hold one electron, and it becomes a hole without an electron. Within an energy band, the density of states is not uniformly distributed. There are fewer states close to the band gap, and the density of state increases with energy further away from the band gap. The distribution of the states as a function of energy is defined as the density of states, which is denoted by D of E as illustrated in the figure here. The expression of D of E for the conduction band and the valence band have already been derived as shown here. But you do not need to worry about it. In fact, we will not be using it in this course. Two more new energy levels are defined here. We denote the lowest energy of the conduction band as EC, and the highest energy in the valence band as EV. With this notation, the band gap energy, EG, is just given by EC minus EV, or the difference between EC and EV. The exact value of EC and EV are not important, as energy is relative. You only need to remember their difference is about 1.1 EV for silicon.